Log on, tune in, find out. Another good idea from Cambridge.
First of all, I'd like to thank the Newton Institute for its hospitality and thank you all for coming this afternoon. I want to talk about solving nonlinear dispersive equations in 2+1 dimensions by inverse scattering, in particular two equations. I'm very mindful that there are a number of experts in the audience, and I will try to adhere to the convention that at least I cite the work of everyone in the room. But this is a small but I hope useful and interesting contribution to a vast subject. So what I'm going to do first of all is tell you what the main results are, and then you can decide whether you want to pay attention to the rest of the talk. I want to say a few general things about how inverse scattering in two space dimensions works, and say a little bit about the history. Again, it's not possible to be comprehensive, but I want to say a few things. And then I'll focus on the properties of the scattering maps, the nonlinear Fourier transforms that are used to solve these equations. Give the applications that prove the two main results, and then give some idea of how I proceed in the analysis of scattering maps. I mean, the scattering maps that I'm going to talk about have been known for a long time. Their applications have been known for a long time. The main issue here is getting certain precise continuity estimates on the scattering maps. And as I'll explain, the key ingredients are actually estimates due to Nachman in his study of the inverse conductivity problem, estimates on multilinear integrals of the Braskamp and Lieb type, and a bit of operator theory. And at the end, I'll throw out a simple question that I don't know how to solve. Okay, so what are the main results? The first result concerns something called the defocusing Davy-Stewardson equation, and Davy-Stewardson 2 equation. Let me explain roughly where this equation comes from. Davy-Stewardson and also Benny and Roskis derived a family of equations which includes this completely integrable equation to describe the behavior of surface waves in shallow water. The solution Q, which is a function of two space and one time variables, and I've used the D and D bar notation, which is very natural in this setting, to write down the equation. So Q is a function of two space and one time variable, and what it's supposed to describe is the amplitude of a wave traveling in a fixed direction with fixed frequency. And so this is a description of surface water waves with weak nonlinearity. And my first result is that this equation is globally well posed in the space you see. And let me just make a few remarks about why this is significant. First of all, I mean, for nonlinear dispersive equations in general, there is a huge literature on well-posedness and a lot of very powerful techniques. This is, to my knowledge, one of the few instances where the inverse scattering method, which again applies to a special case of the Davy-Stewardson family of equations, namely this Davy-Stewardson 2, can get global existence where, at least at present, it seems inaccessible by PDE methods, that is, by methods of harmonic analysis. And the reason is that with the completely integrable framework, which I'll explain, one can get very precise control over the solution that's actually global. Okay, and I'll also explain why I believe this space is roughly optimal for these global well-posedness results. The second result concerns the Novikov-Veselov equation, and here I must, with apologies to the experts in the room, say a little bit about that. The Novikov-Veselov equation one should think of as a two-dimensional analog of the KdV equation, and I'll come back to that point in a minute. And Lasses, Mueller, Siltanen, and Staller have studied in detail the scattering transform based on the Schrödinger equation, which I'll discuss, which formally certainly solves the Novikov-Veselov equation. And they proved a number of nice results on the scattering transform. What remained open until this point, and I will try to explain why it's so hard, what remained open to this point, amazingly, is showing that this inverse scattering transform actually leads, in the case of Schwartz class initial data, to a classical solution. I will explain another route to get to the solution by inverse scattering, which proves that in fact that's the case, and I'll explain how that works. So now let's see, we're considering, or excuse me, Lasses, Mueller, Siltanen, and Staller considered Cauchy data of conductivity type. What the heck does that mean? So we're considering the Cauchy problem for this function of two space and one time variables. Initially we have a function initial datum q depending on two space variables. And such an initial datum is conductivity type if it can be written in the following form, which for a function gamma, which one should think of as a conductivity, which is strictly positive, bounded, and with sufficient regularity so that this expression makes sense. Let's just think smooth and gamma going to one, gamma identically equal to 1 outside a compact set, so that Q is identically 0 outside a compact set. And the name conductivity type comes from the connection of Schrodinger operators of that form, that is minus Laplacian plus Q, with the inverse conductivity problem for this equation in a bounded domain. The inverse conductivity problem, again with apologies to the experts, is to reconstruct the conductivity gamma from the so-called Dirichlet to Neumann map, which maps Dirichlet data on the boundary. And I'm sorry, this is supposed to be U restricted to boundary omega is some F. One looks at the map between those F's and the Neumann data, and one attempts to reconstruct the conductivity in the interior. So what are potentials of conductivity type? I mean, to understand just why this is a hard problem, it's important to understand a roughly equivalent characterization of potentials of conductivity type. And this comes from Schrodinger operator theory, and it says that a potential can be written in this somewhat unusual looking form if and only if the potential Q is what's called critical. That is to say, the Schrodinger operator minus Laplacian plus Q, with Q this conductivity type potential. If the Schrodinger operator is non-negative as a quadratic form, but for any positive perturbation, no matter how small, any negative perturbation, W is positive, but we take epsilon greater than 0 and add a potential minus epsilon W. So I add a little bump. And for a critical potential, just adding that bump means that the Schrodinger operator as a quadratic form ceases to be non-negative, which means it has a bound state. And so the fact of the matter is the potentials of conductivity type form a nowhere dense set in the space of initial data. And that explains why it should be very hard to work in this class, because you try to imagine strategies that are going to work under perturbation. But we'll see that there's another way out. Okay. Yes, it's exactly like the Mura class in 1D. And I'll put up a picture in a minute. Yes, absolutely. Both of these results, so both of the two results, what were the two results again? The global well-posedness for Davy-Stewardson and the smooth solutions by inverse scattering for Novikov-Veselov. Both of those results, as it turns out, are obtained using the scattering transform associated with the Davy-Stewardson equation, which I will define in a minute. The way that we're going to study Novikov-Veselov, taking off on Paul's remark actually, is that there is a nonlinear map proposed by Bogdanov in 1997 that connects the Novikov-Veselov equation in V with something called the modified Novikov-Veselov equation. And as I'll explain, there's an analogy that modified KdV is to KdV as modified Novikov-Veselov is to Novikov-Veselov, and they are connected by analogous linear maps. And that's exactly what one has to do. And the nice thing about the modified Novikov-Veselov equation is that it's solvable using the same scattering transform as is used for Davy-Stewardson. It's in the Davy-Stewardson hierarchy. Okay, so here's the table. This is a way to understand what these equations are, how they're related to certain one-dimensional analogs. I apologize for a certain amount of clutter, but what you should do is read basically two columns, the one space and one time equation, modified KdV here, nonlinear Schrodinger, have their 2 plus 1 dimensional partners, the modified Novikov-Veselov equation, which is also a third order in the space variables, and has a cubic nonlinearity with one derivative. I will write it down once, but that's really all you need to know for the purposes of this talk. The KdV equation in one dimension and its partner in 2 plus 1 dimensions, having a quadratic nonlinearity with one derivative. The nonlinear Schrodinger equation is the 1 plus 1 dimensional partner of the Davy-Stewardson 2 equation, again with an analogous form. Now, what you might ask, since my two results are about this one and this one, what's the third guy doing there? And that's exactly Paul's point, is that this equation is connected to this one via Mura map. It's a simple nonlinear map, and it's not a hard calculation to show that if you take a solution of modified Korteweg de Vries and apply this nonlinear map to it, you get a solution of KdV. This is an old and very famous nonlinear map that connects these two equations. And the range of this Miura map consists exactly of those Q. This is the Miura class, exactly of those Q, so that the Schrodinger operator minus d squared dx squared plus Q is non-negative. If U is U prime plus U squared, then the Schrodinger operator factors into a first order operator in its adjoint. And that's a positive operator, okay? So the point is that there's a similar nonlinear map that takes solutions of MNV to solutions of NV, and its range consists of potentials for which the Schrodinger form is positive. It's exactly the same setup. And it has exactly the same utility. So now I want to say a little bit about what inverse scattering in 2 dimensions means. If people are used to inverse scattering in 1 dimension, there is somewhat of a difference. The good problem in 2 dimensions is a problem at fixed energy. This is an important difference between 1 and 2 dimensions. And in this talk, the fixed energy will be 0. What does it mean for a nonlinear equation like those that I displayed to be completely integrable? So if the evolution equation is q dot equals f of q schematically, so f of q is supposed to be a function of q and its derivatives in space, it's completely integrable if the equation q is equivalent to a so-called lax representation or Markov triple consisting of 3 differential operators, L, Q, and P, whose coefficients depend on q. Think of the q as a function of 2 space variables in time. And the evolution given by this nonlinear equation is supposed to be equivalent to this representation. Now what's important actually to remember about this setup is that L is a linear operator depending on Q, which defines a spectral problem. It will be the spectral problem for L at 0 energy that determines the direct scattering transform. P is a partial differential operator. Those who are familiar with the lax representation in 1 dimension will recognize that this is, in a sense, a kind of weaker version of the lax pairs. And the operator Q determines a time evolution on the scattering data. So this equation is supposed to be equivalent to the evolution equation one's trying to solve. L defines the scattering transform. Q tells you how the scattering data must change with time in order to solve the dispersive nonlinear equation. So as I said, just to put things slightly more concretely, and I will write down concrete maps in a moment for Davy-Stewartson, the linear problem is for 0 energy, and where the spectral parameter will come in, as we'll see and I'll set up, is actually in the boundary conditions on the solution. Typically, the kernel of L is a huge object, and one has to parameterize the solutions in it in some way. That will define a scattering transform which takes Q, and now here you should think of Q as a function of space variables only. For the moment, we're not introducing time, into something R, which is another function of 2 space variables, which is quote-unquote scattering data. And the very amazing fact is that this nonlinear mapping R from the potential to the scattering data, if applied to a solution of the equation, gives something R of t. So now R is a function of both a 2-dimensional space variable and time, and it's the scattering transform of Q of t. And the point is that the evolution becomes linear. Phi of k is typically some polynomial in k. So that if one can invert the scattering map with some mapping I, which goes back from the scattering data to Q, one has an explicit solution formula, or at least as explicit as one can make these scattering maps. And of course, if one has good control of the scattering maps, then one can begin to study in a serious way well-posedness and global existence. I mean, that's exactly the utility of the inverse scattering method, at least in this context. So what do these linear problems, the L in the Markov triple, what do they look like? And again, I emphasize their contributions of a number of people to this, and I'll say a few words about the history in a moment. What the spectral problem looks like for Davy-Stewartson 2 is a problem for a 2x2 matrix-valued function of the 2 space variables, which depends parametrically on a complex variable k. So you should think of, I mean, here and throughout the talk, you should think of k as a complex variable, z as x1 plus I x2. And what's meant here in the exponential is actually the product, okay? So these are solutions which grow at infinity, but they grow in a prescribed way. If you look at what I'm dividing out by, and I'm sorry, one is what this notation means here, and then what follows is the 2 by 2 identity matrix. So what this condition means is that psi grows in a certain way, and if you look at what I'm dividing out and imagine crossing out the potential and considering the free equation, this is something that's in the kernel of this operator. So we're saying that, not surprisingly, that asymptotically, the solution psi behaves like a solution of the differential operator. And what one gets is a family of solutions parameterized by k, and as I'll discuss in a minute, that's what defines the scattering transform. Okay, for the Novikov-Veselov equation, again with apologies to the experts in the audience, the operator L, the linear spectral problem, is the Schrodinger equation, where again one imposes a boundary condition that with a complex parameter in it, zeta. Let me emphasize that the dot products here are real dot products, even though the objects are complex vectors. And in order to wind up in the kernel of this operator, one has to have the complex vector zeta satisfies this condition on the real dot product. It's characteristic to take one branch of that variety, parameterized by k, and one gets a family of solution psi parameterized by x, and I apologize for switching notation in midstream. X is now in R2. And the scattering transform is defined by this explicit formula, which depends on the given potential, on the scattering solution, and an additional factor. So the scattering map in this case is from Q to T. And this is the map that linearizes the Novikov-Veselov equation and has been studied in depth by these people. So let me say a little bit about the history of the D-bar method. Again, I cannot do justice to that long and rich history in a short time, but I want to mention a few highlights. The direct and inverse scattering for the Davy-Stewardson and Novikov-Veselov are both defined via D-bar problems. We'll see, I'll write down explicitly, the D-bar problems that define both the direct and inverse scattering maps for Davy-Stewardson, but this is part of a long development in inverse scattering that begins with Focus and Ablowitz in 1982, Ablowitz-Baryakov and Focus in 1984, who considered the normal Riemann-Hilbert and D-bar problems applied to the KP equation, another dispersive nonlinear equation, which I won't talk about. There's further work of Focus and Sung on the in-wave Davy-Stewardson and KP equations, and work of Beals-Koifman, who initially applied the D-bar problem to 1+1 dimensional problems, and later to 2+1 dimensional problems. And again, given the number of experts in the audience, if someone wants to add or correct my brief history of the literature, I would certainly welcome that. There are some other routes that I would like to talk about for this particular work that I would like to at least mention. I mean, I was inspired to look at these problems by a paper of Percy Daift and Shen Zhou in 2003, which is a very beautiful treatment and very complete treatment of the defocusing cubic nonlinear Schrodinger equation in 1+1 dimension. They really analyze the scattering maps in depth. They get complete asymptotics. And so the question that I began with is, can one do something analogous in 2 dimensions? And another important source of both inspiration and technique is the paper of my colleague at Kentucky, Russell Brown, who in 2001 proved that these scattering maps for the Davy-Stewardson equation are in fact locally Lipschitz continuous from L2 to itself. So that's actually, in a sense, a stronger result than mine, but it's restricted to small data, and there's a good reason why. Okay? But some of the techniques of Brown turn out to be crucial to what I do, and I'll explain that. Okay, now I'd like to get down to work and describe exactly what the scattering map is for the Davy-Stewardson equation. So I recall that the linear spectral problem is this D-bar equation with a boundary condition built in, and where the quote-unquote spectral parameter k comes is in the built-in boundary condition. Following Sung in particular, I want to make a change of variables that first of all takes out the exponential growth, and secondly takes out the mixed D and D-bar problem, and winds up with a different function mu of z and k, which satisfies the following equation. Okay, so here is a live D-bar problem. Mu is a function of z, which is 2 space variables, k, which again is 2 variables, and the shape of the D-bar problem is that mu is determined by d bar data given by q, the potential, and an oscillating phase. And the asymptotic condition now becomes that mu approaches 1 in the space variables at infinity. And now, one should think of this d bar problem as saying that, think of q as a compactly supported function. The d bar u is actually analytic outside a compact set, in particular at the point at infinity. So like any good analytic function, it has a Taylor series at infinity. And the way R of k, the scattering data, is defined is by looking at the first non-trivial term in that Taylor series. So R is defined by the asymptotics of the solution mu. And the map from Q to R is the scattering map. And it's known to be an isomorphism on the Schwartz class. The question is going to be, of course, what about its continuity properties on a bigger set? Okay. On the other hand, there's also an inverse scattering map. If one now takes the solution of that equation and makes a change of variables, which is not too serious, then it turns out that up to this change of variables, the same function also satisfies a d bar problem in the k variable. And the d bar data are exactly the reflection coefficient, again with a similar asymptotic condition. And the way that one extracts the potential, again, is to look at the large k behavior of this function and look at the first non-trivial term in the expansion. And that recovers q. And it's, so again, this is the d bar problem in k. There's really, in 2 dimensions, there's a beautiful symmetry between the direct and inverse problems. They have exactly the same structure, which is very different from 1 dimension. And this defines the inverse map.
1 over k squared in the area?
That's 1 over k squared. I'm sorry. Yes, that's k to the minus 2. Sorry, thank you. Okay. So we now have 2 maps, each of which are defined by d bar problems with essentially similar, with essentially identical structure.
And probably it's not the bar on both of the diagonal terms. I think it's one or the 2 in both, I believe. It cannot be both.
No, I think in my convention it's both. I have a funny convention, but it is both. Okay. Okay, so I mean here's the summary. I'm now going to cheat you a little bit by writing out an integral formula for R of k and Q of z instead of the asymptotic formula. And of course the reason for that is that if one thinks about, the reason for that is quite simple, that the fundamental solution for d bar acts as an integral operator, and the first term is just the integral. And that's exactly where these asymptotic formulas, or where these integral formulas come from, so that the scattering maps continue to make sense even when the asymptotic expansion doesn't. Okay, but these coincide in the case of Schwartz class data. And of course, the lesson is that one needs really good control over these solutions in order to analyze the map from Q to R and from R to Q. Okay, so now let me tell you what my main technical result is. The main technical result that makes these 2 results possible is control over Lipschitz continuity of the maps R and I between weighted spaces. Let me remind you what these spaces are.
Excuse me to interrupt
Yeah.
you one second.
Yeah.
If you be kind enough to go to the previous.
Yes.
This is at least, I believe, with some who have proven that this was okay in the space of Schwartz class, correct?
Yes.
This was our result.
Yes, that's
even,
correct.
Even with large data, because of in this case.
Yes, absolutely, absolutely.
But now you're going to do much better because you're going to work in the H space.
That's right. That's right. That's the point. That's correct. I mean, everything I'm saying about Schwartz class is due to Focus and Sung, and there also is some work of Beals and Koifman. So I should make that quite clear. Okay. So the main technical result is this Lipschitz continuity. And I mean, if there's one thing you should take away from that I would like you to take away from the talk, it's the following idea, that in accordance with this idea that the scattering maps are nonlinear Fourier transforms, it turns out to be very effective to use natural spaces for the Fourier transform to analyze them. I mean, the Sobolev space H11, which remember means that the gradient and a weight times the function are both in L2, is invariant under the Fourier transform. If you go back and look at these maps, remember that, for example, mu22 to the lowest order is just 1. Ek is an oscillating factor, so to lowest order, if you will, this map is just a Fourier transform. So it's the linearization of the map that clues you in as to what the right spaces should be. And these balanced Fourier spaces just turn out to be very effective for this kind of analysis. And so the first result concerns Davy-Stewartson. The second result concerns modified Novikov-Veselov. Let me just remind you that for Davy-Stewartson, or reminder in form, I may not have said so yet. Remember what the inverse scattering method does is it converts, it linearizes the problem. And what happens on the scattering transform side is just multiplication by a phase. The dot here means there's a missing argument, that's the k. And you can amuse yourself by computing the multiplication by this is invariant under H11. Multiplication by this is invariant under H12. That's why these are the right spaces for the problem. Okay, so these are the technical results that allow one to do the job on these two equations. So let me speak about the applications, and then I will speak about some ideas of how these continuity results are actually proved. So first, let me speak about the global well-posedness for the Davy-Stewartson 2 equation. First of all, as background, I need to remind you that Gedalia and So in 1990 studied the entire family of Davy-Stewartson equations, not simply the completely integrable model that I'm discussing. They proved a well-posedness result, which is local in time. And I have to say, what does one mean for a solution to the equation when there are no derivatives in the picture? And the usual thing with a nonlinear dispersive equation is to rewrite the equation as an integral equation using Duhamel. S of t is the fundamental solution operator for the linear version of Davy-Stewartson. Davy-Stewartson is this plus some nonlinear term, which I've schematically called NL. And so the definition of solution in the context of this theorem is that Q of t satisfies this integral equation in the appropriate spaces here. So there is a known theory of well-posedness for the Davy-Stewartson 2 equation. And it's very easy now to take the inverse scattering solution, okay, which is, so here's the formula that I wrote down here, to take the inverse scattering solution and see that it gives the Gedalia-So solution. I mean, this is very regular initial data. So in particular, it certainly lives in L4. And so if you just look at this equation and think about the Lipschitz continuity, then it's absolutely clear that this is a continuous map. And that's well-posedness. End of story. Okay. So that's one of two applications. Now let me talk about why H11 is a good space. And I haven't really talked about the focusing DS2 equation. There's a change of sign in the nonlinear term. For that equation, and let me emphasize that both in the case of Focus and Sung and in the case of these results, there are small data results for the focusing Davy-Stewartson 2 equation. And I mean, at least, you know, in some sense, these methods aren't sensitive until you get into the details, some very important details, to the difference between the two equations in the sense that there's only one key point that I'll explain where the proof distinguishes between the two. So I think it's fair game, therefore, I think, or I would argue, to look at this example by Ozawa, which is a solution of the focusing Davy-Stewartson equation that blows up in finite time and just avoids being an H11, right? I mean, if you look at the gradient and the weight, it just avoids being an H11. And what does blow up in finite time mean? It means that if you look at the mass of the solution, it concentrates at a point in finite time. Then as it happens, it goes on and deconcentrates. But there is a singularity, so there's no way, for example, that you can get a global Lipschitz continuity of these maps in L2, because otherwise this couldn't happen. Okay, and that's why my colleague Russell Brown's result is for small data only. Okay, second application, solving the Novikov-Veselov equation by inverse scattering. Okay, so Bogdanov in 1987 proposed a partner to the Novikov-Veselov equation called the modified Novikov-Veselov equation. And because mathematicians, myself included, can't stand not to write down the truth, I've written down this equation. But I want you to cross this out, ignore it, and think of it in the following way. Okay? That's what it is. And the point, as has been said, is that there is a Mura-type map which connects the modified Novikov-Veselov equation, this thing, and the Novikov-Veselov equation. So what are the key facts that allows one to say something about the Novikov-Veselov equation? The first is that its partner under the Mura-type map, the modified Novikov-Veselov equation, lies in what's called the Davy-Stewardson 2 hierarchy, which just is a fancy way of saying that it can be solved by the same scattering maps as Davy-Stewardson, but with a different phase. Secondly, and I confess this caused me some pain to prove it, if one takes Schwartz class initial data obeying this condition, and let me say just right off what this condition is. It's a fancy way of saying if you write u as a function as u1 and u2, it's just saying that the vector u1, u2 is curl free. It's therefore the gradient of a potential. Okay? So given such a u, and given this additional fact, then the solution u of t of modified Novikov-Veselov equation continues to preserve these properties. Okay? So that's very important. I must have that. That's a separate exercise that I won't talk about. And the third fact, which is really a calculation, is that if u solves the modified Novikov-Veselov equation and obeys this condition for all time, which we know is guaranteed by the initial data, by fact 2, then this object solves the Novikov-Veselov equation. And then finally, the range of this map is basically the potentials of conductivity type. Okay. So, what, without doubt, the strangest of these conditions is this one. What does it actually mean? Okay. So what this equation means is the following. Okay, let's see it. Okay, I made a mistake here. I omitted one piece of the story. I apologize. Let me correct my mistakes in chalk. Okay. Okay. I said that if u obeys this D and D bar condition, which really boils down to a curl-free condition, then u is actually it's actually given by a potential in complex notation. This is just saying u is the gradient of the potential. And this is really saying, okay, so this means that phi is d bar inverse of u. And the fact that u has integral 0 means that phi, not u, is of order z to the minus 2. Okay? Now, so this should have said phi rather than u here. So what this condition really means is the following. If you take the exponential of this function phi, it turns out that this is a strictly positive solution of Schrodinger's equation for this potential q. And what has to be true about that psi, being the exponential of phi, is that it's 1 plus order of z to the minus 2. So what this integral condition is really, it's a condition on the quote-unquote conductivity. I mean, it turns out psi is basically the conductivity gamma with a square root thrown in. It's a condition on the conductivity. I don't know whether this is simply a technical artifact or whether it's a necessary condition, but I need it to make this proof work. Okay, so what are the theorems? The first theorem is that modified Novikov-Veselov is solvable by inverse scattering with the obvious formula, and Importantly, if U is Schwarzschild, then U of t is a classical solution. This is it's a somewhat challenging calculation, but it's a doable calculation using basically the same methods that are in Sung's paper, but making further expansions. Okay, and this has the immediate consequence that if you take initial data of the right type for the Novikov-Veselov equation, one gets a classical solution of Novikov-Veselov just by chasing it through the Mura transform. Okay, and so that answers a question that was posed by these authors. Now, I should remark that one has to make an argument that my inverse scattering method is the same as LMSS's inverse scattering method. That's a doable argument, but I won't go into it here. Okay, so having told you about the two main results, having told you the core technical results regarding the scattering maps, I want to give some idea of how they're proven in the last roughly 15 minutes. Okay, so these maps, recall, are well defined on the Schwartz class by asymptotic expansions. So I've actually said a few times before in the talk, one has the explicit formula for the fundamental solution of the D-bar problem, which leads to integral formulas for R and Q. So these are the maps that one wants to study, the direct and inverse scattering maps. The challenge then is to get very good estimates on the solution to the D-bar problems. And now I want to talk about some of those key ideas. So the first thing, very natural standard thing to do, is to reformulate the D-bar problem as an integral equation. We know what the fundamental solution for D-bar is as an integral operator. So instead of having the D-bar problem with an asymptotic condition, I reformulate that problem as an integral equation with the following integral operator. The first piece of it is the fundamental solution for D-bar. It's convolution with the fundamental solution for D-bar. And the next piece of it is just the right-hand side of the equation. And the question is, can this integral equation be solved? The answer, of course, is Fredholm theory. So what are some of the basic properties of this map that one uses? What are some of the analytic inputs to analyzing this integral operator? One of them is the Hardy-Littlewood-Sobolev inequality for integrals of this sort, which gives mapping properties of D-bar inverse. These are not hard. They have the following implications for the operator t, depending on the potential q and the complex parameter k, that enters into the integral equation. And what's very nice here is how nicely these estimates work out when q is in H11. I mean, this really is a clue somehow that one has the right space. First of all, I mean, easy, one doesn't need H11 for this. It's a mapping. It's a good mapping from LP to LP. It's even smoothing, so it's a good compact operator. It maps into Helder continuous functions that vanish at infinity. So it's certainly compact as a map from L infinity to itself, which is where I'm going to solve these equations. The solutions are constructed in L infinity. Now, this is precisely the point where defocusing enters, is the proof that in fact the operator you want to invert has empty kernel over L infinity for all possible values of the parameters.
This is the generalized function argument.
Yes, exactly. I mean, this again is a well-known argument, which has been in the literature for some time. If you take the
we first learned from Bekua, but maybe.
Okay, yeah. That's.
But maybe people knew it before.
Yeah. So if one looks at the condition for a vector to be in the kernel, it corresponds to a homogeneous D-bar problem, and one can do the following thing. So first of all, one notes that any psi in the range of this operator, because of its smoothing properties, is actually in a nicer space than L infinity. And secondly, one has, I mean, I say Brown-Newman, but true, this goes back to Bekua. For any distribution solution of an equation of this form, d bar u is au plus bu bar, if one has the right kind of regularity on the solution and the coefficients, one can prove that u actually vanishes. One should think of this as a kind of a generalization of Liouville's theorem. It's that kind of vanishing theorem. And the equation is set up exactly to do that. If you look at the sum of these two solutions, you can write the differential equation for the sum in exactly this form with a equals 0. And so you get that the kernel of this operator you want to invert is empty. But that's what happens. What's the difference between the focusing and defocusing case is an infuriating minus sign right there. And once that minus sign is present, the whole argument falls apart, and it has to, because there are, in fact, non-trivial solutions, and I'll talk about some at the end of the talk. Okay, so then by Fredholm theory, we have a compact operator. We know that identity minus the operator has trivial kernel. And we therefore know, in fact, by some standard stuff with the second resolvent formula, that this map is locally Lipschitz. But that's not good enough, because we have solutions that depend parametrically on K, and we want to control large K behavior. And this is where the first key estimate comes in, this Nachman type estimate from Nachman's work on the inverse conductivity problem. And that's really the following estimate. If you look at the square of this operator as a map from LP to LP, it decays as K goes to infinity. Let me remind you what this operator looks like, so that one can kind of think about this stuff as I'm talking. Remember that the operator consists of two parts. That there's the fundamental solution for d bar, but what it's operating on is this function, which is oscillatory, an oscillatory function of z and k. So the key thing is that one has a somewhat singular integral plus an oscillatory part. And one expects that for large k, the oscillations are going to give some decay in the norm of the operator, and that turns out to be exactly the case. Now, this is a good thing because it tells you that for very large k, the operator, you can always invert the operator you want to invert in the integral equation. And really the key thing is that if you conjugate the d or d bar operators by this oscillatory factor, you get something which, when applied to sufficiently regular objects, exhibit decay in k. And a Q in H11 allows you to manufacture a sufficiently regular object. Okay, so by the difference of two squares formula, in some sense, this means that the original resolvent is invertible, and it means that the solution I get from inverting this operator is bounded uniformly in k. That's still not good enough because we really want sharp estimates on these scattering maps. So now I just do a very simple thing. I do a finite expansion whose leftovers will be controllably small in k. Okay? So that means I can expand the solution, and it's going to take the following form. There's going to be an identity term. And if I put that into the inverse scattering formula, that's going to correspond to a Fourier transform of the potential. Then there's going to be the end part, which there's so much decay in k, who cares what the rest of the stuff is doing? That's controlled. Then there's the stuff in the middle, which corresponds to a finite number of iterations of that integral operator. And this is where the second major estimate comes in. Okay, so again, just to recap, if I take this expansion and put it into the formula that defines the map, I get a sum of terms. There's just a Fourier transform up to a linear change of variables, something that's controllably small because it corresponds to this remainder, and then something in the middle. So the only thing that's left to do is tell you what to do with the something in the middle. What the something in the middle is, being an iteration of integral operators, is an integral that's multilinear in Q, has various somewhat singular factors, integral but somewhat singular, and lots of oscillation coming from these factors. So what do you do with a multilinear integral with lots of oscillation? And the answer, which I learned from my colleague Russell Brown, is the following. There's a very simple trick that if you want to prove an estimate on, so what you have in rather schematic terms is an integral of something that depends parametrically on k. Actually, let me say in the following way that, let me just again make a kind of a schematic problem. This isn't exactly what it is, but it's something like this. Except, yeah, let me. So f is a function of lots of variables. Phi is a linear function of the various x's. And this is Cn, but I'll say Rn. What do you do to capture the mapping properties? What you do is you multiply by a test function in K and integrate. And then you get a multilinear function of f, which is my stand-in for the q's and all this other stuff, plus the Fourier transform of psi. And that, so what that leads to is considering multilinear forms where you have all the stuff you had before, then instead of an oscillating phase, you have some function which is the Fourier transform of a test function. Now, the key thing is that Brown is able to estimate such multilinear forms and gets exactly what one wants. Okay, one gets that the multilinear form is bounded, first of all, with respect to the right norm of the test function, and secondly, with respect to the right norm in the potentials. So that means that the integrals that occur in the pieces of R corresponding to these intermediate terms all define bounded functions in L2 if Q is in, all define functions in L2 with respect to the K variable if Q is L2 in the original variables. This is really the other key thing, is these multilinear estimates. Okay, so now in order to control the map from Q to R in the way that I want, that is to H into H11, I also need to look at the maps from Q to the gradient of R and from Q to R times a weight. And it's exactly the same story if you exploit the d-bar equation and integration by parts and use exactly the same techniques. And it just works out in the correct balanced way. Again, a sign that this is really the right space for this problem. And it's these techniques that give the proof that the direct scattering map from Q to R is Lipschitz continuous. Okay. And the second technical result that I mentioned is just a refinement of these techniques. You need some more weights and some more derivatives, but it's really the same idea. Okay, so that actually ends the main exposition, and I want to close with a really annoying problem. So what happens in the focusing case? In the focusing Davy-Sturtson equation, it's possible for soliton solutions to occur, and the signal that this can happen is that this operator need not be invertible for all k. And here's a very simple example. This is the simplest example of a one-soliton solution for Davy-Sturtson that I know. Solitons for Davy-Sturtson have algebraic rather than exponential decay. They are unstable, so in a certain sense they're uninteresting, but it still would be nice to understand in this sort of framework how they evolve and to see the instability. The soliton solutions were found by the people listed. And
we already have some such lamp solutions in our original paper.
Okay. Okay, so I stand cheerfully corrected.
But I'll make a remark later about them.
Yeah, okay. So what is the signal? The signal is that the homogeneous equation corresponding to the kernel of this operator has non-trivial solutions. And the exceptional set is non-empty. Now, what I want to say about the exceptional set, this operator, the one sitting down here, depends in a smooth but not analytic way on the parameter k, which means that everything you know about analytic Fredholm theory is totally irrelevant to this problem. And that's what makes the study of exceptional sets so hard. Okay? All that we know is that this set is closed and bounded, but at least I don't know anything else about it. One would expect for these one-soliton solutions that the exceptional set ought to be a point. I don't know how to prove that either. I would know how to prove it if I could solve the following problem. This is the system that corresponds to the statement that the kernel of the operator you want to invert is non-empty. You can easily check that it has these solutions. If you want to show that the exceptional set consists of one point, all you have to do is show that up to maybe trivial symmetries, these are the only solutions, and that would do it. So far, I've been totally unable to do it. Straightforward problem, can't do it. And on that humiliating note, I will end the talk, and thank you for your attention. Questions, comments?
I I'd like to make a remark,
Yep.
if you allow me. First of all, of course, this is a very, very nice result, and when we did this work with Sang that you mentioned, already at the time I posed this problem to him,
Mhm.
you see, and I'm very, very happy that finally it has been answered. But let me make a remark about these last parts
Yep.
of your talk,
Yep.
because I would object to the use of the word soliton
Yeah.
in the following sense. You see,
Okay.
why are solitons important?
Mhm.
Solitons are important, in my opinion, not because they are explicit solutions like this.
Mhm.
Solitons are important because they are the natural asymptotic state of the system.
Yeah.
Which means that if you look at the KTV and you start with a hump and you wait for a long time and you say what will happen to this hump will decompose into solitons.
Right.
So there now, from the mathematics point of view, you see that very important because they correspond to the discrete spectrum
Yeah.
of your maps.
Yeah.
You see? So what happens now? In more dimensions, unfortunately, for the D-bar cases that you have studied,
Mhm.
we have never been able, in the cases where we expect that that maybe there is discrete spectrum because the generalized function fails, we have never been able to do this. Therefore, we don't have a spectral characterization of such solutions. That's why, in my opinion, the solutions are irrelevant. It's not, and of course, that's why they are unstable. They have nothing to do with they're not deep. They understand. They're not fundamental.
Yeah.
You see.
Yeah.
Now, the only case that perhaps it would be interesting for you to look at some point,
Mhm.
the only case where we do have a spectral characterization for such localized solutions
Mhm.
is the work we did again with Mark for KP1,
Uh-huh.
where we have lumps,
Okay.
and there the lumps are the eigenvalues of a
Mhm.
certain Fredholm operator.
Mhm.
But this is very, very tricky business.
Yeah.
It's not in L2, it's somewhere between.
Yeah.
So you probably will have to work very, very hard in order to embed these creatures
Mhm.
in the rigorous theory. But it should be done because numerics, for example, show what you expect. So numerics, who have done this, is if you start for KP1 with a localized solution,
Mhm.
you go to lumps.
Mhm.
So there are
Mhm.
these lumps are the correct solitons.
Uh-huh.
And I don't know, but my intuition is that they don't exist such creatures for Davis-Stewartson.
Mhm.
Davis-Stewartson, by the way, with the numerics, there was another paper we did it. I was Prof, I didn't do anything, I just gave some advice because I'm not good in numerics, but we looked for Davis-Stewartson 2, the one you have just studied,
Mhm.
and indeed, everything happens what you expect. Namely, if you start with a nice localized solution, and you wait long enough, numerically you see it decomposes. It doesn't go anywhere, it doesn't have anywhere to go. So from this point of view, you have this contradiction between beauty in mathematics. So what you have done is very beautiful, but in some sense,
Mhm.
less interesting because this problem is like linear. You see, Davis-Stewartson 2 behaves exactly like linear equation. You see, in other words, anything will disperse away.
Yeah.
And while if you could have these lumps, and as I said again, the only case we have a spectral characterization of them is for KP1,
Mhm.
then this will be a true nonlinear model
Mhm.
in the sense that you will have some nonlinear effect to see.
Yeah. Yeah.
That's what I would say.
What about line solitons, for example, for KP2?
No, line solitons, of course, they're okay, but they're not, they're unbound, as you know, they don't have finite energy. So
Uh-huh.
they're not localized creatures. I mean, they're,
Yeah.
in that sense also, they're not good. You see?
Uh-huh.
If you go to boundary value problems, I mean, as you know, for Davis-Stewartson 1, we have these beautiful things called dromions.
Yeah.
You see, but again, they are artificial. And my only hope is that, more than hope, is that if you go to boundary value problems,
Uh-huh.
now then these artificial things become generic. So, in my opinion, boundary value problems for multi-dimensional equation will be much richer because you will be able to get these localized structures.
Mhm.
Otherwise, what we do is very beautiful, what you have done especially is very beautiful, but it doesn't behave nonlinearly.
Mhm.
You see? Namely, there's no difference between Davis-Stevenson
Yeah.
2
Yeah.
and the linearized version.
Yeah.
You see?
Well, in fact, I've looked at a paper of Kiselev where
Yeah.
he gets leading asymptotic behavior for defocusing Davis-Stevenson 2. And not only, in terms of the scattering data, it seems to evolve almost exactly like the linear problem. There's not even the logarithmic phase shift you see in one-dimensional
that's right.
NLS, for example.
That's it. That's it.
So, yeah. So I agree.
But anyway, the problem you solved is very good. And as I said, I've been waiting for this now for many, many years. So thank you very much.
Yeah.
Maybe you said it already, but the restriction to these conductivity type initial states, this is a real restriction or just somehow just what the method allows you to?
Do you want to take that one?
There is a conjecture that it seems that with these conductivity type potentials, there are no exceptional points or singularities in the scattering data. And there's a conjecture that such singularities, when they appear with some non-conductivity types, would correspond to Soliton solutions. But this is just written somewhere in a paper by Boiti and others, and there is no rigorous backing so far.
Not clear then.
Not clear, unfortunately.
Yeah. No. Once it's absolutely right that in a sense these are the easy problems. What I was looking for was to establish a kind of functional analytic framework for studying the Mets, but defocusing DS2 is an easy problem, and I wouldn't go so far as to say that conductivity type for NV is an easy problem, but the dynamically interesting stuff somehow is yet to be analyzed, and it's very hard because analysis when these exceptional sets are non-zero and you can't invert the operator is very hard. In the case of both of these equations, precisely for the fact that the integral equation you want to study is not susceptible to analytic Fredholm, and you really have no idea what the structure of the exceptional set is. That makes it interesting.
By the way, for the colleagues that have been coming to the seminar, there was another Novikov mentioned a couple of weeks ago, has nothing to do with this Novikov. This Novikov is the big Novikov, is the big medalist. While the earlier Novikov is the young Novikov, the son of Henkin.
Roman.
Yes.
Okay.
I first met him in 1982, Novikov, and I didn't know at the time there were so many comments, so I asked him, you're the son of Novikov? He says, no, Novikov is my teacher. He was a student of Novikov. My father is Henkin. You see, but because he's Jew, his father is Jew, so he took the name of the mother, not to have problems with the guy. So he's the son of Henkin, who's a noted mathematician as well, of course, but took the name from his mother.
Okay. Any other questions?
Thank you very much.
Observations? So,
Thank you.
thank you.